So let's first finish the theorem, the statement of the Berger holonomy theorem from last lecture. So assume a manifold, Riemann manifold is complete, m-dimensional, and assume it's not locally symmetric and not nuclear product. Then we have a classification of the possible restricted holonomy group of the metric. So we talk about four types. So the first one is the generic one. So the holonomy group is SOM. Second one is Kähler case. The holonomy group is UN. And the third case is the case when the holonomy group is SUN. This is a special case of the Kähler case, the Calabi-Yau case. And then we will talk about the case of SPN, and that's a subgroup of SU2N. So this corresponds to the hyperkähler case. It's an even more special case of the Calabi-Yau case. And now there are a couple more. So next possible one is SPN dot SP1. So this is best and this is called quaternionic Kähler. Kähler. This is best understood as it's here again. M is 4n. So you consider Rm as a n-dimensional quaternionic linear space. Now we talk about, so then this SPN is essentially just GL and H. So it acts on the left. But the quaternions is not commutative. So there is also right action, and you take SP1, which is just the unit the unit quaternions. So it's just it's a 1-by-1 matrix. So it's just one quaternion which preserves the norm, so that it has to be unit. So this is this X on the left, and SP1 X on the right. So you get so this is the action of SPN dot SP1. So such a space is called quaternionic Kähler. This is not Kähler. This is not a subgroup of, because you have this right SP1 action. It's not Kähler. It's not Kähler. It's different. And so this number 4 and 5 are related to quaternions. So number 6 is then there are two just isolated examples. The previous example, they appear in families. There's a parameter n. Here is just one as the G2. This is a subgroup of SO7. It's defined as the automorphism group of the octonions, right? SO7. Where this octonions is Cayley numbers are 8, and it's not even associative. But as it's a number system, you can consider it's a ring, can consider automorphism group of this O. Then it's a subgroup of SO7. That's the G2 group. There are other ways to define, but this is the um, easiest to say. And then this group called spin 7. Spin 7 is by definition that abstract group is a double cover of SO7. But here we view it as a subgroup of SOH. So it's again so SOH is eight-dimensional space. It's a space of octonions. So it's a subgroup of the special orthogonal group acting on octonions, and it's generated by right multiplication by imaginary unit octonions. So it's like a imaginary number. So the octonion or quaternion, it contains the real numbers, and then the rest. So here is 7-dimensional imaginary octonions, and then you consider unit elements there, norm 1 elements. So you consider the right multiplication by them on RH, the octonions themselves, and then this generate a group called spin 7. I mean that if you want a really better understanding of these groups, then you need to do more work. So here is the complete list given by the Bourget theorem. I mean, the original Bourget theorem contains some other groups, but which was later shown to be either cannot exist, or it has to be the holonomy group of a symmetric space. But here we're assuming it's not symmetric. But the remark is that our topic is Einstein matrix, but we were talking about holonomy, and then the point is this is closely related. So so let's start by this. One. So we call a MG called special holonomy. So the first two is not special. If holonomy group is belong to or let's say it's special ones SUN SPN SPM SP1 or G2 spin 7, which contained as a subgroup. So the point is that the first one is generic. If you just give a arbitrary given Riemannian metric, it will have special. You will have a SOM holonomy, and the second one is scalar. But in this scalar setting, is also kind of flexible. If you have studied scalar metrics, so it's locally given by partial bar of a function. So that function has freedom. It's also not very special. And this Calabi-Yau metric, they are special kind of scalar metrics. We will talk about more about scalar metrics later. But here the point is that these special ones, they are Einstein. They are all Einstein, and these two, maybe not. This four cases is Ricci flat. They're all Einstein. They're more special than Einstein. They're Ricci flat, and this one is known to have non-zero Einstein constants, lambda g, lambda no zero. So this having holonomy group of special is closely related to constructing Einstein matrix. They gave special examples of Einstein matrix, and actually, most examples of Einstein matrix, they are related to special holonomy or Kähler geometry. Most known examples. Say. So they are special and they're actually easier to construct than general Einstein matrix because you have extra structures to study. And the second one is that so if we want examples of, I mean, so Bourget list just gives a constraint, and then you want to construct examples of all these metrics with this special holonomy. For generic holonomy, it's okay. For Kähler, just we know there are Kähler metrics. And if we want compact examples of special holonomy metrics, that's not easy, and they will and not non-locally symmetric. It kind of in this Ricci flat case, it basically just says non-flat, non-splitting. So this is known for all of them except no, but except this case, Quaternionic killer. This is still a open question. So compact Quaternionic killer manifold, four M dimensional. So there are no examples where the Einstein constant is positive. In that case, the known examples, they are all symmetric, nuclear symmetric. And that I don't think there is any example known about the negative Einstein constant. It's still a open question. If you want to learn more, you can look up references. Anyway, so this finishes the statement of the holonomy theorem, and it's also finishes our claim that in general dimensions, the Einstein matrix, the interesting cases are Einstein matrix and with extra structures. Next, I would like to go back to the dimension 4 case. And here we know that Einstein matrices are not necessarily constant sectional curvature, they are flexible. And we want to construct, write down some examples of 4-dimensional Einstein matrix, which are the hyperkiller, and that's an ansatz construct given by Gibbons and Hawking, the physicist. But before that, we want to review some 4-dimensional geometry that's very special. 4-dimensional geometry. So we know that in general, if you study Riemann geometry m-dimensional, there's a so the curvature tensor, you have a curvature tensor, and this curvature tensor, you write Rijkl, it has some symmetry, and it can be viewed as a element in the curvature in mapping lambda 2 to lambda 2 symmetric endomorphism. Uh, um, or it can be viewed as a bilinear form on lambda 2, right? So it's because the first two component indices, it's anti-symmetric, and the second one is also anti-symmetric. But you view this together, Ij and Kl can be swapped together. So the action is explicitly defined. So if you beta equals beta Ij, say Ei wedge Ej, then there's R acting on beta. There's another two form, Ij be some this Ij component defined to be 1/2 R Ij Kl beta Kl. This 1/2 is because this beta is we're summing over all indices, so it's better defined this way, so that this R Ij Kl is really just R acting on Ei wedge Ej inner product with Ek wedge El. So it's this you can view that as endomorphism, and the remaining curvature tensor we have a decomposition according to the representation of SOM. It's composed as a scalar curvature part 2n and minus 1 g. This Krukani-Nomizu product plus 1/2. Sorry, m. 1 of m reach circle g plus w. Okay, so what are they? So the reach circle is a traceless Ricci tensor. So it's just the Ricci tensor minus its trace. And W is the wire tensor. It's conformal invariant object. And this the Krukani-Nomizu is sent to symmetric two tensors to a curvature type tensor. Right. So let me write what it's let's say Kasai is a symmetric two tensor, sim2 lambda 1 eta sim2 lambda 1, then Kasai eta. This will give you IJKL. I think you must have seen this. It's just a Kasai IK eta JL plus Kasai JL eta IK minus Kasai IL eta JK minus Kasai JK eta IL. So it satisfies the symmetries of a curvature tensor. Okay, so it has three parts. And so this is in general dimension. This is what we do. Now, in dimension 4, the special thing is that this number 2 has a further decomposition. Okay. Dimension 4. Now we assume we always fix orientation. So when we talk about the 4-dimensional matrix, we have to choose an orientation. So this is because once we fix orientation, we got a Hodge star operator from lambda 2 to lambda 2. It's Hodge star. So it's alpha wedge star beta equals the inner product alpha beta E mu G. You can take this as a definition, but then the point is that a star squared equals 1. and it's a symmetric operator. So it composes lambda 2 into eigenspaces, lambda plus, direct sum, lambda minus. These are objects where star alpha equals alpha, here star alpha equals negative alpha. So this is called self-dual. Your dual is self, and the other part is anti-self-dual. So I think this is just a linear algebra, right? I think it's good to write down things explicitly. So it's not difficult. So if you fix oriented orthonormal basis or frame, let's say EI, then lambda 2 is just EI wedge EJ, and then this lambda plus and lambda minus, lambda 2 are 6-dimensional. Both lambda plus and lambda minus are 3-dimensional. And the basis of lambda plus is of this form, omega, E1 wedge E2 plus E3 wedge E4. We call this omega 1. E1 wedge E3 plus E4 wedge E2 is omega 2. E3 plus E1 wedge E4 plus E2 wedge E3. So it's easy to memorize it. So just fix E1 and then the permute is 2, 3, 4. And you can easily check it because the star of one summon is the other one. And then you have omega 1 bar. This is anti-self-dual. It's a minus sign. So at each point, we can always choose bases like this. Okay. So this is a very important factor about 4-dimensional geometry. Many interesting things related to this, and in terms of groups, it's really also related to the fact that SO4, SON, but n bigger than 4 is simple, but SO4 is not simple. It is double cover of SO3. So locally, it decomposes as product of two groups. So the way to understand this is that if you have any orthonormal transformation of the tangent space, it induces orthonormal transformation of the bundle of two forms, and it preserves each component. And each component is 3-dimensional. So you have this map, and then you can show this map is surjective, and it's 2 to 1. Okay. So because lambda 2 decomposes, then the corresponding curvature transformation, it's the one we defined previously, then we're decomposing into block matrices, right? You can write as 4 components, and then this is this effect that the 4 components can be written in the following form. I don't know when I use this S for scalar curvature, or maybe R for scalar curvature. R over 12. Traction is rich. It's symmetric. So this W plus W minus, they are self-dual and anti-self-dual part of Y curvature defined as follows. So you just take W plus acting beta. It's just you take W acting on beta, and then you take the self-dual part. 1/2. And W minus, you just take the anti-self-dual part. So what does this mean, right? Well, the content of this is really, is, in other words, it says that the following. First, it's traceless. So maybe there's scalar curvature. Maybe change it to R. So you have 3 terms in the curvature tensor. We need to understand how these 3 terms act on each on the 2 form, self-dual or anti-self-dual form. So the first thing we know is that this this is in general dimension also true. So G, the product G, this is the first term. That's a coefficient which is what? That's R over 2m m minus 1. That's 2 times 4 times 3. That's 24. R over 24 times this, right? So we just need to understand how this acts on a 2 form. Or in more generally, because we also have the Richet, and let's just consider if you have something which is eta G, eta is another symmetric 2 tensor acting on some 2 form beta is IJ. By definition, it is have some L AJ delta basis, right? Just delta IJ eta KL minus eta I, sorry, let's rewrite eta IK delta JL plus eta JL delta IK. So this is just I mean, this is definition. How do we do this? 4 terms. So you want to make it symmetric in IJ, in IK and JL, but then you want to be anti-symmetric in I and J and K and L. It's J I L delta J K minus eta J K delta I L. But then you multiply by beta K L. After the sum, it's easy to see this give you that is eta IK minus eta JK beta KI sum over K. This is very simple. Okay. So in particular, the G, if eta equals G, it acts on beta IJ. That's just delta IK. That's just beta IJ minus beta IJ. So that's twice beta IJ. So that's why this first term scalar curvature over 24 G. This goes to R over. It acts on 2 forms, just a multiple of identity. It's twice identity. So that's okay. This part is easy to understand. And then we want to say that the traceless Ricci, it swaps the self-dual 2 forms and the anti-self-dual 2 forms. Traceless Ricci maps lambda plus minus 2 lambda minus plus. Yeah, I think it's good. We do some computation. Just want to tell you. I mean, it's a completely elementary linear algebra, but you just need to do a computation once. So, so how do we do this? We want a basis. We want to know what is this traceless acting on lambda plus minus, but we know what is lambda plus minus basis for this. But this traceless Ricci, is a little complicated, but at one point we can always choose basis so that this means just like choose the trace matrix is another symmetric matrix. It commute with G is identity, right? So you can simultaneously diagonalize it. So we may assume this trace is Ricci is diagonal in the basis number 1, number 2, number 3, and it's traceless. So number 1 plus number 2, number 4 plus number 4 equals 0. Okay, so then we can go to the next page. So traceless Ricci G. Okay, this acting on beta to ij. This will give you by the formula before. This this formula. Now eta is the traceless Ricci, and this is diagonal, so you know that it has to be multiple of delta ik. Similar to this, but with a coefficient, and what you get is lambda I plus lambda j, beta ij. For each term, there is a there's coefficient, right? The traceless Ricci. So now, if we want to know this acting, for example, on omega 1, this self-dual, one of the orthonormal bases of a self-dual part. So what is omega 1? Omega 1 is E1 wedge E2 plus E3 wedge E4. So that means beta 1, 2 equals 1. Number 1 plus j. Okay. Number 1, number plus number 2. Ij equals now, let's just get rid of this ij. So together it becomes E1 wedge E2. Okay, so it acts on E1 wedge E2 is given by multiplied by this coefficient, and then E3 was multiplied by this coefficient. Easy. So this is okay. Anyways, E3 E4. The point is that acting on beta ij is multiplied by this. So but then we use the fact that it's traceless. So this is negative number 1 plus number 2. So this is just number 1 plus number 2 times omega 1 bar. To change the, which is E1 wedge E2 minus E3 wedge E4. So it maps omega 1 to omega 1 bar is similarly maps omega 2 to omega 2 bar, omega 3 to omega 3 bar. Similarly, so it maps lambda plus to lambda minus, and similarly, it maps lambda minus to lambda plus. Lambda plus, lambda minus, lambda minus. So that's why the traceless Ricci appears in the off-diagonal term. Next, the wire curvature. This is a little more complicated, but we can also do. So what does this say is that the wire curvature maps lambda plus to lambda plus and lambda minus. So preserves the type, the duality type, and it's trace free. So this is important, interesting. So this is exactly the decomposition of this 3 by 3 matrix, 3 by 3 matrix as a trace matrix plus a trace free matrix. Okay. So and here the important thing is for wire curvature. We know that it is in the kernel of the Ricci contraction. So the wire curvature satisfies IK equals 0. Sum over k, right? So this is what we can use. Let's do this. It's not very complicated. So W, for example, we want to say it maps lambda plus to lambda plus. So but lambda plus and lambda minus, they are orthogonal. So maybe do we mention this? So this is orthogonal decomposition. Let's put it here. Orthogonal. This is because of this fact. Or you just see it from this this form. The lambda plus and lambda because star square this linear algebra decomposition into eigenspace. So we just need to show that lambda x on lambda plus its inner product with lambda minus equals 0. Right? Plus. So let's just do take one example, and the rest will be similar. So this W acting on omega 1 is it's IJ component. What is this? This is so it's 1/2 W IJKL, and then it's omega 1 KL component. But omega 1 has only 1, 2, and 3, 4. And then you just get a Wij 1, 2 plus Wij 3, 4. Right? And again, this 1/2 becomes because you have repeat you have 1, 2, and 2, 1. Same. So then this W acting on omega 1 and omega 1 bar, you take the inner product. And so this has a IJ component. So this is the IJ component, this, and this has only E1, 2 minus E3, 4. And then you see that this becomes W 1, 2, 1, 2 plus W 3, 4, 1, 2. This is the first part. And then you have subtract with the 3, 4. W 3, 4, 3, 4 plus W 1, 2, 3, 4. Confusing. Maybe it's better. Okay, so this part you take this E1 what E2 minus E3 what E4. Okay, so you first pairing with this, you get a 1, 2, 1, 2 plus 1, 2, 3, 4, and you subtract 3, 4, 1, 2 plus 3, 4, 3, 4 becomes W 1, 2, 1, 2 minus W 3, 4, 3, 4. This is equal to this, right? Symmetry. So we want to show this is 0, and this is a exercise using the fact the wire has Ricci contraction equals 0, and so this says if you fix 2 indices, you will sum over the other indices over from 1 to 4, you get 0. So for example, you can fix this third one So and the first one, and that the fourth one vary. 1 2 1 2 plus 1 3 1 3 plus 1 4 1 4 equals 0. And then I can fix this the second and the fourth one. 1 2 1 2 plus 3 2 3 2 plus 4 2 4 2 equals 0. This I do the same for the dot 3 4. So 3 1 3 1 plus W 3 2 3 2 3 4 3 4 equals 0, right? And then I do 1 4 1 4 2 4 2 4. So this is a W I K J K, right? K. Here is I fix first term. I fix I equals J equals 1. Second term I fix K equals L equals 2. I equals J equals 3 equals L equals 4. Okay. Just play with this, and then it's not difficult. So if you sum over the first two terms, the rest is 1 3 1 3 1 4 1 4 2 3 2 3 2 4 2 4. Subtract this, you sum the third and fourth, you get the same thing. So that's why you get this equals 0. And I think it's a good exercise. This is 0 to check the rest. So check that W omega I with any omega J bar equals 0. Omega 1 with omega 2 bar, and that the W plus and the minus, the trace is 0. It's just elementary linear algebra. Okay, so this is four-dimensional geometry. So and the whole thing depends on the orientation. If we change orientation, we will change number the plus and the minus, number the minus, and we will change W plus and W minus. Just remark. Changing orientation is W plus and W minus. Sorry, number plus and number. So, but orientation, I mean, so when we talk about things, we need to fix the orientation. So, let's just take the convention of the when we talk about any four-dimensional Riemannian manifold, we always fix orientation. So why now how is it related to Einstein matrix? So first, there are some obstructions to four-dimensional Einstein matrix. There are some four-dimensional characteristic classes which you can relate this curvature to topology. Via characteristic classes. Two. So if MG is compact, okay, and the first one is the Gauss-Bonnet Chern. This is SS Chern gave a high-dimensional generalization of the Gauss-Bonnet formula for surfaces, and in 4 dimensions it has particular nice formula that 8 pi square of the Euler number. So here these coefficients are important if you want to do precise computations. So Euler number of m equals the integral over m. So This does not use this self-dual anti-self-dual decomposition, but just the decomposition of the curvature and the Pfaffin. You can write the Pfaffin in terms of this d mu g. So in particular, if the matrix Einstein, G is Einstein, implies that this term is 0, so chi has to be non-negative and equal 0 if and only if m is flat, G is flat. This is clear. If it's 0, then the scalar curve is 0, the y curve is 0, everything is 0. So this already give you abstractions of some 4-dimensional. It's similar to the 3-dimensional case, but the 3-dimensional we can just use the fact they have constant curvature. In 4 dimensions, if you take a genus G surface times S2, right? So this Euler number, compute is 2 times 2 minus 2G. So this is less than 0 if G is bigger than 1. If you take a hyperbolic surface times a round S2, this will not admit an Einstein metric. So this is a Gauss-Bonnet term. Then the next one is signature formula. So now again, so M is compact. So similar to the self-duality, we have the second cohomology of M. Take a integer homology. That's a cup product, right? This is cup product, and by Poincare duality, this is non-degenerate pairing, symmetric pairing, or unimodular, better. Symmetric pairing. Particularly, it's not. If you take R coefficient, then it will be non-degenerate pairing. So so it's a symmetric bilinear form. So it has a signature. And so that signature we denote by sigma of M. Okay, just a number of positive eigenvalues minus a number of negative eigenvalues. Again, here you need the orientation. And then maybe generally use tau. Okay. And then a signature formula is Hilbert signature formula. 12 pi squared tau m. And this is usually is given by integral of a the first Pontryagin class, and here Pontryagin has only depends on the wire curvature. While W plus squared minus W minus squared mu g. So one can combine this these two together, the Gauss-Bonnet term and the signature formula together, because they both have both have wire curvature. So this W plus square plus W minus square, right? So you can combine them. What you get is called a Hitchin-Thorpe inequality. This is so better than the Gauss-Bonnet term. But signature formula itself does not constraint Einstein matrix. It's just about Y curvature. It's a conformal invariant. Okay, so it's 2 chi plus 3 tau equals 1 over 4 pi squared m. And then you cancel W plus minus square, you get only W plus squared plus squared over 12 minus traceless reach squared d mu g. And if you do 2 chi minus 3 tau, you get a 1 over 4 pi squared m 2 minus W minus squared. Basically, it is just, again, just a matter of orientation. And then the point that if it's Einstein, again, traceless reach is 0, it implies that 2 chi plus 3 tau 0 plus minus 3 tau equals 0. So this is called a hitting top inequality. There's also a characterization of the equality case. If we have time, we may get, but let's just do this. And this already rule out some examples, like if you take a CP2 four dimension, this has forbidden student is Einstein, and it has Euler number. Euler number is 3, and the signature is 1. Okay. But you can take a P CP2, and you connect some with Q CP2 bar. CP2 bar which just means you change the orientation. So the point that's just talk. Maybe we don't even need this. Just for simplicity, just connect sum of P CP2s. So when you connect sum, the signature just add together, and the Euler number essentially when do the connect sum, the second homology add together, but the 0 and the top homology does not change. So basically, when you have P CP2, then the tau will grow like P, linearly in P, coefficient 1, right? The chi is also like P. And then it will violate this inequality because this 2 chi has to be bigger than 3 tau. If they both are like P plus some constant, then this cannot be true. So I don't know. You can this is P large. You can check maybe P equals 2 is already a problem. P equals 2. This is 2 is 6, and chi equals 4. P equals 3. That's 9. Anyway, you can check the P large, no Einstein. Not very large. So this is this already give you obstruction. This is better than the just Gauss-Bonnet chain itself. And then so this is just for our own purposes, or for my own purposes, four-dimensional Riemannian matrix. We define a type into three types. Three types according to W plus. So we know that W plus is 3 by at each point is 3 by 3 symmetric traceless matrix each point. So it has three behaviors. Either it's identically 0, so or one. It can have three distinct eigenvalues. It has two distinct eigenvalues, or just one eigenvalue. If it has only one eigenvalue, because it's traceless, it has to be identical to 0. So type 1 is W plus generically identical to 0, so it's always 0. So this is anti-self dual. means it has only anti-self-dual component of wire curvature, and the self-dual part vanishes. And type 2 means that the W plus generically has two distinct eigenvalues. Type 3 means that it has generically has three distinct eigenvalues. So this we will, I think in today we will explain more about this anti-self-dual. So it is a conformal invariant condition. W plus equals 0 is conformally invariant. But if you want the Einstein metric, then Einstein equation is not a conformal invariant, right? But this conformal invariant condition, it is very closely this is a theory of Penrose. It's a twistor theory. If you just care about anti-self-dual structure, there's a twistor theory. So, for example, which four manifold admits a Riemannian metric with anti-self-dual wire curvature? That's called the anti-self-dual manifold. There were a lot of study of this, and this condition is can be characterized into a complex geometry condition. So it's not very much related to the main topic, but since we have 2 more minutes, let's just say a little bit more. So that if you have any four manifold, we have lambda plus. This is a three-dimensional real vector bundle. But if you consider the unit spheres in lambda plus over M, so this is a six-dimensional compact, six-dimensional manifold, compact, 6D, dimension 6, real manifold, and it has a canonical almost complex structure. So this almost complex structure is defined. So at each point in this sphere bundle, so there's the tangent space decomposed into the horizontal part and the vertical part. The horizontal part is identified with the tangent space in 4 dimension, and the vertical part is the tangent space of a sphere. So on a 4-dimensional space R4, of course, we have a almost complex structure. But then if you just define this arbitrarily, you don't get a global almost complex structure. However, on this bundle, you can use this S2 to adjust it, to twist it. That's why it's called twistor space. This is a twistor space. So it has an almost complex structure. And the W plus equals 0 is exactly equivalent to saying that this J is integrable. So you get a three-dimensional complex manifold. And this complex manifold, so it's a relation between 4-dimensional this is anti-self-dual geometry and complex three-dimensional geometry. For example, there are many results. You can interpret result between this. So Taubes prove that any group can be finally generated represented group is a fundamental group of a 4-dimensional self-dual manifold, and then correspondingly, so it can be the fundamental group of any 3-dimensional complex manifold. So this is an important topic, but it's a little bit related, but we will not talk about much details later. So let's take a say 5 minutes break. Okay. Okay, so now we will consider Einstein matrix. In particular, the easiest case is when we consider Ricci flat matrix and W plus equals 0, anti-self dual Ricci flat matrix. So this is a hyperkiller matrix. So we defined a hyperkiller in terms of polynomial before, but now another way of defining this is in 4 dimension. Is we have the curvature tensor as W plus R over 12 versus Ricci W minus plus R over 12. So if we want the metric to be Ricci flat, implies traceless Ricci equals 0, R equals 0, and also anti-self-dual, then W plus is also 0. Then what's left is just one component. Everything else is 0, 0, 0. It's only W minus. Such metrics, anti-self-Ricci flat matrix, such metrics locally will be hyperkiller. Why? This is because essentially this curvature. I mean, we decompose the curvature of the remaining metric into these 4 pieces, but this first part is actually essentially the same as the curvature of the induced curvature or the curvature of the induced connection on lambda plus. So if everything is 0, then the lambda plus is flat. So locally can find a called parallel trivialization or parallel orthonormal basis of lambda plus. And now so we can make it everywhere. So you have the so there will be 3 forms: omega 1, omega 2, omega 3. These are 3 self-dual forms. We form a triple. Omega bar is the triple of 2 forms, self-dual 2 forms. And each one of them is parallel. Again, parallel implies it's closed. So in particular, it is a closed form. And at each point, so we have this model when we talk about the self-duality. At each point, we can choose orthonormal basis so that omega 1, omega 2, omega 3 are of this form. But if omega 1, omega 2, omega 3 satisfy this form, then you can see that omega I wedge omega j, because just or you can by the definition, the omega I wedge omega j is same as omega I wedge star omega j. So this is just delta ij volume form d mu g. Okay? So, that means here when we say it's a so omega I is also omega I wedge well omega j is the same as omega I wedge star omega j self dual. So it's omega I omega j d mu g delta ij d mu g. Okay. So this is such a triple of two forms satisfy these two equations. Each of them is closed, and they are kind of form the wedge product give you a identity matrix. Such a triple is called hyperkiller triple. So why this is hyperkiller? So we know lambda plus is flat. Okay. So so maybe one way to see this is that we write as SO4 is a double cover of SO3 times SO3. Let's see what is so for general four-dimensional Riemannian metric, the holonomy group will always be containing SO4, right? So it will induce corresponding parallel the action. So the holonomy is given a tangent vector. It comes out with tangent vector. It's action on the tangent space. So it induces the corresponding action on lambda plus and lambda minus. But lambda plus is flat, right? If you have a flat vagabond locally, if you do parallel transport, it will just go back to itself. There's no curvature, right? The standard. So that means it will the holonomy group, the restricted holonomy group, will have to map to the image will be contained in 1 times as trivial times SO3. So this corresponds to lambda plus. The Bell's lambda plus is flat, right? And then it's a simple exercise. This is SU2. So SU2 is a subgroup of SO4 that maps to one of the SO3. This is here is a where you see this is to identify R4 identify with C2, and then you can write down what is lambda plus lambda minus as before. So you can SU2 is the action C2, and then you can just explicitly check that the SU2 is exactly the one that preserves lambda plus. So in terms of complex geometry, we write lambda plus the basis before, but in terms of complex geometry, lambda plus is maybe we just the next page just do it in a little bit more detail. Then if you are R4 that C2, right? The lambda 2 is you can complexify lambda 2. Then there's a complex type lambda 2 0, lambda 1 1, lambda 0 2. So lambda plus actually is generated by the if you fix a this means you fix a complex structure. So so this is G, the standard metric G corresponding to the killer form omega. So this is the form generated by omega, and the real part of lambda 0 2, and lambda minus is a primitive part. So it's omega orthogonal inside lambda 1 1 R. The real value the 1 1 forms. R means it's invariant under conjugation. So then SU2 is exactly the one the containing SO4 is exactly the and it's acting trivially. lambda plus y, because SU2 is defined as um, as a transformation that preserves complex structures containing GL2C, right? It preserves the complex structure, and so it preserves, or it's the same. Preserving you already preserve the metric G. Preserving complex structure is the same as preserving omega. So it preserves omega. Preserves omega, and it's determined equals 1. It preserves this capital omega. DZ1, what's DZ2? That's the real part. 0, 2, or 2, 0. We change to 2, 0. It's the same conjugate, right? It's just by definition. So under this map, SO4 to SO3 times SO3 minus this SU2 gets mapped to 1 times SO3. And also there's a group U2, then U2 mapped to the subgroup of SO times SO3. Anyway, you can, but the key point is that lambda plus is flat, then the holonomy group will be containing SU2, and this is Calabi-Yau four dimension, right? Okay. But SU2 is also equal to SP1. This is low dimension. All these things are identical. They're all equal to S3. As topological manifold is just a three-dimensional sphere. Yes. This is SU2 is three dimension. It's the same as quaternionic unity quaternions. And the complex structure, you can write if you want the classical hyperkähler definition, the complex structure is because each omega I is a parallel two form, so it defines and it defines a complex structure. So omega j equals g times ij composed with ij. Then it's I1, I2, I3. These are three complex structures. This also define a hyperkähler structure. You have many ways of viewing this. But the point is that this condition that the traceless reach equals 0 and W plus equals 0, or lambda plus is flat, is equivalent to, it implies the existence of such a hyperkähler triple. And I want to say that conversely, you can use this hyperkähler triple to characterize such metric. And then when later, if we can write down some two forms to satisfy these equations, we will get a hyperkähler metric. And that's the point. So conversely, given a hyperkähler triple, given a triple omega bar, omega 1, omega 2, omega 3, satisfying the equation d omega j equals 0, j 1, 2, 3, omega I, which omega j equals delta ij d mu g. Then we want to say this is such a metric G. G is satisfies Ricci equals 0, Ricci flat, and W plus equals 0. So it's equivalent. Okay. So first, um, 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 the point is that um, maybe I think number we want to remember here we're given a Riemann metric G, but one can check that first. Check that lambda plus is spanned by omega 1, omega 2, omega 3. This use the fact that so if I just from omega 1, omega 3, we can define a new metric. So how do we do this? This is because so at each point, no, each point, we can make a omega 1, omega 2, 3. And then so this is a maybe one. So you want to say that they are all they are all also um so you can use you can maybe a better way to see this. Let's see. You can define. You can check the Riemann metric G satisfies the formula GUV equals 1/6 IJK epsilon IJK iota U contracted with omega I which iota V contracted omega J contracted omega K divided by d mu G. So yeah, we want to um oh, here is that we need some fact about number of 2. If you're given omega 1, omega 2, omega 3, if you're given this triple, we can write down a metric G in this form, and this G will agree with your remaining metric G. So the G given. So in some sense, let's see, omega 1. So these omega i's, they are also normal with respect to the wedge product, right? So they form a um, they form a basis of they span a three-dimensional subspace of um the they form a three-dimensional subspace of um of lambda 2 which is a positive, but then positive three-dimensional subspaces of lambda 2 is you can always um, maybe let me do it more precise. It's a bit confusing. So maybe we do it later. It involves um this lambda. Sorry, the three-dimensional positive three-dimensional subspace in lambda 2 is x transitively by the corresponding induced map by SL4. But anyway, let's I think it's better. Let's accept this fact. If we have time, we will do it today. But otherwise, we will explain the detail in next time. But let's accept this fact that if you have this triple, then you get this, and G will be Ricci flat and W plus equals 0. Then we have a characterization of hyperkähler matrix in terms of hyperkähler triples. So we want to let's do the Gibbons-Hawking, and as promised, we want to construct some examples. So these examples will not be compact, unfortunately, but they are either complete or the local models. These are important if you want to understand the singularity formations of this matrix. So what is this? So you start with a three-dimensional R3. You take a domain omega in R3. Let's assume this domain first. Let's assume this domain is contractible. Okay. With the standard coordinates in R3. Then you can take a positive function on omega, which is harmonic. Okay, Laplace V equals 0. And then because the Laplacian V equals 0, this is the same as saying D star dV equals 0. In terms of harmonic, this is a flat space. So Hodge Laplacian equals 0. So that means star dV is a closed form, and if it's contractible, it's D of a one form. There exists one form theta. Pick this. So and then we work on this P equals the product as 1 times omega. This is a four-dimensional space. And now we can write down, it has a standard projection to omega denoted by pi. So we have write down a standard, a Riemannian metric G is on P. It is very simple. You just take the standard coordinates Euclidean metric, do a conformal change by V. So because of this projection by pi, everything downstairs forms tensors, this symmetric tensors matrix you can pull back to P. So this is degenerate, but then you add a term on the S1 fiber, it's a dt plus theta squared. Here the t is a coordinate on S1, standard coordinate on S1. You view it as R mod Z. So we claim this is hyperkähler, and this is the Gibbons-Hawking answer. So you start with a positive harmonic function in three-dimensional, then you will get a hyperkähler metric in 4-dimension. So why it is true is the point. The here we don't even need the factor we talked about before. So because we can just write down explicitly a self-dual, 3 self-dual 2 forms. Write down hyperkähler triple omega. So let's denote this by capital theta. Okay. So then omega 1 equals v dx dx1 dx2 plus dx3 wedge theta. What I use theta. Omega 2 equals v dx2 dx3 plus dx1 wedge theta. Omega 3 equals v dx3 wedge dx1 plus dx2 wedge theta. So here, it's easy to check that omega 1 I wedge omega j, for example, omega 1 wedge itself, you just get a v twice, you just get a twice v dx1 dx2 dx3 wedge theta, right? So this is 1/2 delta ij d mu g. So here maybe I forgot this is 1/2 somewhere. Omega I does not, if you write that in this form, does not have norm 1, it has norm square root of 2, right? Yeah, because okay, in okay, sorry. So the in the linear algebra here, where is that? Yeah, so here there's 1/2 here. It is because you take omega 1 squared, you get twice E1, E2, E3, E4. It's twice of the volume form. This is a minor thing, but better to make this precise. So in any case, by the definition of G, d mu G is something like dx1, dx2, dx3, theta, and you have with 1/2, with 1/2, with 1/2, with the next 1/2, so it's just V, right? This is the volume form, and this is true. So this is the algebraic part of the equation, right? And d omega I, that's is 0. Let's just check. D omega 1 is is dv wedge dx1 wedge dx2 plus dx3 wedge d theta. Okay. And then this is 0 exactly because star dv equals d theta. Everything. So here there's no t component. Everything only depending on the x1, x2, x3 variables, right? So this is just a say v3, and then here you get d theta, the 1, 2 component. And that's exactly given by this 0. Okay. So by the fact I said before, it is hyperkähler, but actually we can this metric, this omega 1, omega 2, omega 3, they are self-dual because star, you can compute the star omega I equals omega self-dual. And because we know explicitly what the Riemannian metric is, right? a star of V. I mean, you have a basis which is a V to the 1/2 oriented basis V to the 1/2 dx1, V to the 1/2 dx2, V to the 1/2 dx3, and V to the negative 1/2 theta. This is the basis. This is like this is exactly what we before. This is like E1 wedge E2 E3 wedge E4. So it is self-dual. So once we know it's a self-dual, we can write down use complex geometry, a little bit more complex geometry, but we have time. So here in this special case, we can let's check. It's hyperkähler. So capital omega denoted by omega 2 plus I omega 3. So claim this is decomposable. So this is square root of -1. This is a decomposable two form. Decomposable, meaning that it can be written as gamma wedge gamma prime, where gamma is a one form, complex one form, valued one form. It's true in general, but in this particular setting, it's easy to write down, right? So this is what is this omega 2 plus? It's a V dx2 minus square root of dx1 wedge dx3 plus dx1 plus dx2 wedge theta. So this is a dx1 plus I dx2 wedge theta. Minus square root of -1 v dx3, something like this. It is a product of two one forms. Okay, and it's closed. So such as saying, it will define a complex structure. So how do we define? Define a complex structure, almost complex structure. To define almost complex structure J, we just need to specify what is a 0, 1 vector field, right? Define this T 0, 1 of M could be complex tangent vector fields such that X contract omega equals 0. So one can check here because this is locally this model. You can see that the dimension, this rank is 2. Or is 1 as a complex sorry complex two-dimensional. This is just pointwise use model. Because again, I write this as E1, E2, E3, E4. This is you can just check. This linear algebra, okay, the exercise. But then the point is, this is we claim this is integrable, and this is because omega is closed. Okay, and this is involves checking if you take two vector fields, gamma t 0, 1, m, then their bracket is still in, right? So we need to say that if x, y both satisfy this, then we want the bracket of x, y equals 0. But this is just some algebraic some simple manipulation. So x the bracket y, that's the bracket of x, y along x contract y, and then this is the same as the bracket of x y contract omega minus y contract x y. So the derivative satisfies Leibniz rule. Okay. This is 0. Sorry, this is 0. First term is 0. Y contract omega is 0 everywhere. But this is also 0. Why? Because this is by Pachon formula, right? X contract omega plus X contract d omega. X contract omega is 0. D omega is 0. So everything is 0. This is 0. Okay. This is shows that the complex structure is integrable. Okay. And again, using the local the algebraic manipulation, one can see that the omega 1 define omega to be omega 1. This is actually Kähler with respect to this complex structure J. One thing we know it has to be of the form 1, 1, 1 because omega 1 wedge omega 2 omega is omega 1 wedge omega 2 plus square root omega 3. This is of course 0 by definition, right? So this is so omega. All right, but by definition omega will be of the form 2, 0, type 2, 0. That's why define this 0, 1 have to be contracting with this omega. There is a whole, you can think of that it should be a holomorphic two form. And this little omega, omega 1, that's the Kähler form. Because omega is Kähler, d omega is 0, right? Omega j. And Kähler form, we know that omega is actually parallel. Omega 1 is parallel. And d omega is 0. It's holomorphic to, so in particular, partial bar omega is 0 is holomorphic. It's holomorphic two form. So this is by choosing omega, capital omega to be omega 2 plus I omega 3. You get that this is 0 to lambda omega 1 is 0. But similarly, you can If you choose omega to be omega 3 plus I omega 1 or omega 2 1 plus I omega 2, you will get that nabla omega 2 is 0. Now this is completely symmetric in term in omega 1, 2, 3, right? So if one of the probably everything is parallel. So this implies that lambda plus is flat. It's generated by this 3 parallel two forms. So it's a Ricci flat, and W plus equals 0 is a hyperkiller. So in this case, I mean, not in this case. So I think for this we only use the fact that this metric is sorry, this forms are self-dual with respect to metric. So this is sense has to be justified. I would probably only do it next time. But for this particular Gibbons Hawking answers, I think we have all the details. Okay. The point is that we have this mechanism. Now, how do we generate examples, right? So if you the simple examples is just product, right? If you just take V to be constant, so V equals 1, then what we get is R3 times R1, which is theta to be 0. So but then the point is that this kind of thing is not a very interesting if we just work with product of S1 times a domain. There's no topology. Sorry, the topology is too simple. The interesting topology is when you allow omega to be non-contractible, right? Just more generally. So allow the omega R3 general domain may not be contractible. For example, a punctured ball. But in this case, there's a problem. You have V again harmonic omega. For example, this will include the case of Green's function, right? Then you have a positive Green function on the whole R3. I mean, with a pole at the point, but you can remove that pole. It's a perfect function. But then you have a problem. You want star dv to be d theta. This is no longer true. Laplacian v equals 0. So this is closed, but the closed form may not be exact, right? Especially if for example, omega equals R3 minus a point, you have the non-trivial H2. However, this is what electromagnetism or U1 gauge theory, right? So you have a if you have a close two form, if it's integral plus, if it's in if 2 pi of it is defines a integral cohomology class, then locally you can write as a D of a one form, and globally you can realize as a curvature form of a U1 connection. So then there exists a principal U1 bundle, S1 bundle, P over omega, and a connection, U1 connection, theta. So it is a so theta. So previously I write little theta, right? D theta equals star dv downstairs on omega, and then just lift it. Now you cannot do it downstairs, but you can do it upstairs. So theta is a perfect defined one form on P. It's a connection one form, so it is a one form on P, and locally it is satisfies as d theta equals star dv, right? With curvature. Maybe the connection you better to write as a square root of -1 theta. this as a connection with curvature star dv. Okay. So the point is you have this closed form. Locally, you can write as one form, and then locally you can live with the upstairs, and then you want globally, you want the upstairs, you can glue together well defined one form, theta. Okay, this is topological condition. You can do it by hand. If you want. So this integrability condition is important. And then once you have this, you can just do the same thing. G equals v dx1 squared plus dx2 squared plus dx3 squared plus v inverse theta squared. Okay, so locally, it's exactly the same situation. And the main point is that this little theta is not unique, right? And all the discussion before that this G is hyperkiller, it's exactly the same because we only use the local form. So this is makes things much more interesting because now I can do example on omega is R3 minus 0. I get a V, and it's something 1 over R, and in order that condition to satisfy it, it has to be k has to be a non-positive integer, so that this star dv is in H2. Okay, the individual condition is given by this, and then we will get a hyperkiller metric on some S1 bundle over omega, and then you see when you have the singularity, the v goes to infinity. So what is the geometric meaning of v, right? You go back to the definition here. It's v inverse theta square. So this connection one form, it acts, his value takes value 1 along the generator of the S1 action. So the S1 orbit will have length. So the length S1 orbit, length v to the negative 1/2. So that means this goes to 0 as r goes to 0. So this corresponding to a fixed point of the S1 action. So by the way, so these metrics we wrote down, they all have naturally invariant under the S1 action, right? S1 invariant, because it does not really depend on the rotation. So here is also S1 invariant. So this metric has an S1 action, isometric action, preserving the hyperkiller structure, and the orbit tends to 0 at this point. So in other words, the singularity of V corresponds to a fixed point locus of the S1 action. And that's why the topology could be more interesting, because if you have free S1 action, then just the products twist the product. But then when you have a fixed point, then it's interesting. And the local model is given by the following. We have the standard R4, okay, flat metric. This, of course, is hyperkiller. It will identify with C2. Then we will have a standard S1 action. Let's see. You have a standard S1 action, and the quotient will give you R3. And this map Z1, Z2 is defined as real part, Z1, Z2. Imaginary part, Z1, Z2. 1/2 d2 squared minus d1 squared. Okay. And this action, this S1 action on C2 is given by e to the I theta, e to the negative I theta. Okay. So these are not these are not randomly chosen. It's actually correspond to, so on C2 we have omega 2, omega 1, omega 2, omega 3. This hyperkähler triple standard triple, two forms. And these objects are moment maps, hyperkähler moment maps. Moment maps. Oh. This is a moment. I don't remember which correspond to which omega j. I mean, there might be some reordering, but it's a moment map. And geometrically, this is just given. So you view R3 as a cone. So R3, you view it as a cone over S2, right? A lot of S2. And your R4, you view it as a cone over S3. And then along, so each fiber is just a map from S3 to S2. That's the hop vibration. This is a map from R4 to R3, just a cone over the hop vibration. And then the point is that this is the corresponding. You can write this as in terms of Gibbs-Hawking answers, and the V is exactly 1 over 2R. So, right? So when K equals 1, so that means but if you, the fact is that if V behaves like 1 over 2R plus something smooth, yeah, R equals 0, then this P can be compactified by adding 1 point, the fixed point of the S1 action into a smooth hyperkähler metric. So even though V is singular, the corresponding metric, it can be compactified. Then the local model is given by this by this R4, okay, flat R4. So this is the local model, and if V behaves like K over 2R plus smooth, and K is bigger than 1, then what we get is as orbifold of type C2 mod ZK. So this is model, and then once you have this, but we still haven't write a new metric. It's just flat metric, right? Now that's the next one. So example is just very simple, because all this condition, right, involves star dv. That's just derivative of v, right? I take the 1 over 2r. I just add 1. Then we will get we can just use the same theta as the theta you get for R4. And then what we get is a new hyperkähler metric on R4. New rich flat metric. It's not flat on R4. And this is what's first discovered by this physicist top knot metric. Okay, there's 4 names, right? Top and UT. Each of them is the initial name of some physics. Okay, so this top knot metric also lives on R4 because the same S1 bundles. But it has a different geometry from the flat R4 because the behavior as R go to infinity is very different. For R4, when R go to infinity, V goes to 0. Remember that the length of the S1 orbit is inverse of V. So it goes to infinity. This Hopf fibers go to infinity. Here, when R go to infinity, V goes to 1, does not go to 0. So that means Hopf fibers do not grow. So at infinity, it's not a four-dimensional thing. It's actually a three-dimensional thing. It has a cubic volume growth. So I think time is up for today. Next time, in the first half, I will continue write down more examples of this. This is I think this is a very interesting geometry. It's not I don't think it's taught in standard Riemannian geometry. It should be.